Hi everyone, welcome to lecture 11 of solitons. So last week we started looking at conservation laws, and in particular we focused on conservation laws for relativistic field equations. And what we found is that there exists a few very special relativistic field equations, namely in addition to the Klein-Gordon equation, which is linear, there were three nonlinear relativistic field equations, the Liouville equation, the Sine-Gordon equation, and the Sinch-Gordon equation, which admit extra conservation laws in addition to the conservation of the topological charge, energy, and momentum, which, as we mentioned, are rather general. In particular, we found that the Liouville equation, the Sine-Gordon equation, and the Sinch-Gordon equation admit a conserved charge of spin 3. And I also mentioned that it's possible to show that there exists infinitely many more hidden conservation laws, but we decided to stop there, and you will study next term a more systematic method to find all these extra conservation laws for relativistic field equations of so-called integrable types, such as the equations that we studied at the end of the last lecture. So what we'll do instead this week is to try to construct conservation laws for the KdV equation. This is section 4.4, conserved quantities for the KdV equation. So let me remind you that the KdV equation is the following partial differential equation for a function u, the field, the function of t and x. So the KdV equation is ut plus 6u ux plus u equal to 0. And we impose boundary conditions for the KdV equation on the real line, such that u, ux, uxx, so all higher x derivatives, vanish as x goes to plus or minus infinity. And we can start by making a very simple observation that the KdV equation is already written in the form of a continuity equation. Indeed, we can write the KdV equation as a partial derivative of u with respect to t plus a partial derivative with respect to x of 3u squared plus uxx equal to 0. So we can interpret u as a conserved charge density and 3u squared plus uxx as associated current density. And since the boundary conditions imply that the current J tends to 0 at special infinity, both plus and minus infinity, we deduce that the charge Q1 given by integral over space of the charge density, which in this case is equal to U, is conserved. And the physical interpretation of this conserved charge is as the mass of the water wave. The integral of U is nothing but the area under the profile of the wave. And if you assume that water has a constant density, the mass of the wave will be proportional to this area. So the charge Q1 is proportional to the mass of the wave. Good. We found the first conserved charge where the charge density rho was equal to u. So next, we might want to try rho equal to u squared. So let's check if a continuity equation holds for the charge density rho equal to u squared and a certain current density. Let's then calculate the time derivative of u squared. That's 2u ut. Next, we can use the KdV equation that tells us that ut is equal to minus 6 u ux minus u xxx. So that's equal to minus 12 u squared x minus u. The first term is already a total x derivative of minus 4 u cubed. Whereas the second term is not a total x derivative. Let's write it again, minus 2u x. But we can write the second term as a total x derivative of minus 2u uxx. At the price of adding a correction term, which we obtain by moving a derivative from uxxx to u. So we'll get plus 2u x u x. These are the kind of manipulations that we do when we integrate by parts. And now we notice that this final term, 2ux uxx, is also a total x derivative of ux squared. So we can write everything here as a total x derivative of minus 4u cubed minus 2u x plus ux squared. The quantity in brackets is then the current density J associated to the charge density rho equal to u squared. And since J tends to 0, both at minus and plus infinity, thanks to the boundary conditions, we found that the charge defined by integral over x of u squared, let's call that charge Q2, is also conserved. This is equation 4.27, and the physical interpretation of the integral over space of u squared is as the horizontal momentum of the wave. The first conserved quantity integral over u was proportional to the mass of the wave, and the second conserved quantity integral of u squared is proportional to the momentum of the wave. Since we found that the integrals of u and u squared are conserved charges, we might want to try next a charge density rho equal to u cubed. Let's introduce some convenient notation, namely use an equal sign between quotation marks to mean equal up to a total x derivative of a function which tends to 0 at special infinity. Using this notation, we find that the time derivative of u cubed is equal, by the chain rule, 3u squared ut. Next, we use the KdV equation to write this as minus 15 u cubed ux minus 3u squared ux x. Now the first term is already a total x derivative. And the second term will be equal up to a total x derivative to 6u ux x when we move an x derivative from uxxx to 3u squared and pick up a minus sign doing that. At this point, we can use the KdV equation again, because the second term in the KdV equation is 6u ux, which appears in the expression that we just found. So we find that the expression that we just wrote is equal to minus ut plus u x. These are the first and third term of the KdV equation, and that multiplies u x. Now, uxxx times uxx is also a total derivative of 1/2 uxx whole squared. And we can also write the first term minus ut times uxx up to a total derivative as utx. If we move an x derivative from uxx to ut at the price of a minus sign. Now, this is not an x derivative of something, but it's in fact the time derivative of 1/2 ux squared. Therefore, if we rearrange and we put this final expression back to the left-hand side, we find that Q3 given by the integral over x of u cubed minus 1/2 ux squared, the integral, the partial time derivative of the integrand is equal to the partial x derivative of a function which tends to 0 at infinity, and therefore Q2 is also a conserved charge. This is equation 4.28 and has the interpretation as being the total energy of the wave. The integral of u cubed minus 1/2 ux squared is proportional to the total energy of the wave. Here are these first three conserved charges, proportional to the mass, the momentum, and the energy of the wave again. Now here is an exercise for you. Calculate the value of these three conserved charges for a KdV soliton, which is a one-parameter family of solutions which depend on the parameter v, the velocity of the wave. And in particular, you should be able to find that Q1, which is proportional to the mass of the wave, is proportional to v to the power 1/2. And you should be able to find the proportionality factor. Q2, proportional to the momentum of the wave, turns out to go like v to the power 3/2. This is in agreement with the fact that the momentum for non-relativistic object is the mass times the velocity. And finally, the total energy of the wave, Q3, is proportional to V to the power 5/2, in agreement with the fact that the kinetic energy of a non-relativistic object goes like the mass times the velocity squared. All this is for a KdV soliton of velocity v. Now please pause the video and do this exercise. And when you're done, come back. Now, it turns out that these three conservation laws (4.26, 4.27, 4.28) of mass, momentum, and energy follow from some obvious symmetries of the KdV equation by Noether's theorem. And therefore, they're not unexpected. By the way, these obvious symmetries are as follows. So for the mass, this corresponds to the symmetry by a shift of the field U. For the momentum, it corresponds to the symmetry by a shift of the space coordinate x. And for the energy, a shift of the time coordinate t by three constants, c, c prime, and c double prime. All right, so the conservation of mass, momentum, and energy are not really a surprise if you know Noether's theorem. But the surprise is that Miura, Gardner, and Kruskal in 1968 were able to find 8 more conserved charges of the KdV equation, and they found these 8 more conserved charges by hand. And all but one of these 8 extra conserved charges, the exception will be studied in exercise 23, take the following form. Qn, what's called the conserved charge, and conserved charge is an integral over space of u to the nth power plus corrections. For example, the fourth conserved charge is Q4 integral over x of u to the fourth minus 2u ux squared plus a fifth uxx squared. The fifth conserved charge, Q5, is the integral over space of u to the 5 minus 5 u squared ux squared plus uxx whole squared minus a quarter uxxx squared. And then there are a few more conserved charges up to Q10, which is integral over space of u to the 10th power minus 60 u to the 7th ux squared plus 29 more terms plus a final term, which is 1 over 4,862 times u with the 8x derivatives squared. This is equation 4.29. I should say here that there is some logic to the expressions for the conserved charge densities, which are integrated. And the logic has to do with the scaling properties of the KdV equation that you studied in an exercise in the first assignment. So if you're interested in that, I'm happy to say a bit more during office hours. But for now, let's just accept these conserved charges. And if you want to do another exercise, you might want to pause the video now and, for instance, derive Q4, starting from rho equal to u to the 4th power and then adding correction terms. So the result of Miura, Gardner and Kruskal is quite surprising and rather interesting, but it raises a few natural questions. So we have conserved charges Q1 up to Q10, so it's then natural to ask, are there infinitely many more conserved charges? And the second question is, if so, is there a systematic way to find them? You won't be surprised to hear that the answer to the previous question is yes. There exists infinitely many more conserved charges, and there is a systematic way to find them. And this is what was discovered by Gardner, again in 1968, which was the golden year of study of solitons and also of many other things in the world. This leads us to section 4.4 and this systematic way to find more conservation laws for the KdV equation uses this idea called the Gardner transform, which is, I should say, a very clever idea, but as we'll see, it may appear rather unintuitive, at least at the moment, but later on in this course, you'll understand where it all comes from. All right, so what is this clever idea? Well, we'll get there in a number of steps. We'll start first by supposing that the field U is a function of x and t can be expressed in terms of another function v of x and t as follows. So U is lambda minus v squared minus vx, where lambda is a real parameter. We'll call the relation between U and V equation 4.30. Now let's substitute equation 4.30 in the KdV equation for U to find the following. The KdV equation is 0 equal to ut. U is lambda minus v squared minus vx, partial differentiate with respect to t, plus 6 ux, so we get plus 6 lambda minus v squared minus vx times lambda minus v squared minus vx, x derivative, plus uxxx, that's lambda minus v squared minus vx, partial derivative with respect to x, 3 more times. Then you need to partial differentiate and multiply a number of things and hopefully simplify. When you do that, you should be able to see that the resulting expression can be written as minus the differential operator 2v plus partial derivative with respect to x acting on vt plus 6 lambda minus v squared times vx plus v x, x, x. I'll leave it to you as an exercise, and this is exercise 24 in the problem sheet to work out the algebra. Please stop the video now and make sure that you agree with the final result. Welcome back. So to summarize, the KdV equation for the field U is equivalent to equation 4.31 for the new field V. And in particular, if V solves the equation, which is obtained by setting the expression in the square bracket in 4.31 to 0, namely Vt plus 6 lambda minus V squared Vx plus Vxxx equal to 0, then U, given by equation 4.30, solves the KdV equation. As I'll stress later, the converse is not true, but definitely if V solves equation 4.32, then U given by equation 4.30 solves the KdV equation by construction. Here's where we are. If U is related to a new function V by equation 4.30, then the KdV equation for U is equivalent to equation 4.31 for V. Let me make a remark here, which might not be particularly enlightening, but it's important for historical reason. Equation 4.30, the relation between U and V, simplifies when lambda is equal to 0. In particular, the relation between U and V was previously considered by Miura and was known as the Miura transform. Earlier in 1968. And in that case, equation 4.32, which I remind you was the equation that you get when the quantity in the square bracket in equation 4.31 vanishes, becomes the wrong sign MKBV equation. That you analyze in the context of traveling wave solutions in exercise 13.2. Mind you, the wrong sign MKdV equation for V is Vt minus 6V squared Vx plus Vxxx equal to 0. Okay, when lambda is equal to 0, we get something which was known before, the wrong sign MKdV equation and Miura transform. So what? Well, at this point, Gardner's idea was to bring the resulting equation, in this case the wrong sign MKdV equation, to a form closer to the KdV equation. And in particular, Gardner proposed to take the new field V to be equal to epsilon, a third field W, plus 1 over 2 epsilon, and the real parameter lambda to be equal to 1 over 2 epsilon all squared for some real constant epsilon. This is equation 4.34. So why would you want to set B and lambda to this expression? Well, because then lambda minus V squared, which appears in the relation between U and V, is equal to 1 over 2 epsilon all squared minus epsilon W plus 1 over 2 epsilon all squared. And so we get that this is equal to minus W minus epsilon squared. W squared after a cancellation of the squares of 1 over 2 epsilon. And therefore, U, which was equal to lambda minus V squared minus Px, is now equal to minus W minus epsilon square W square minus Vx, which is minus epsilon Wx. This is the so-called Gardner transform, which relates the original KdV field U to the new field W. I'll use GT for the Gardner transform. And in terms of the new field W, the KdV equation for U, or equivalently equation 4.31, which we derived earlier for V, becomes the following expression. So first, let's start from equation 4.31 for V. First, we have the differential operator 2V plus d by dx, and that becomes, in terms of W, 2 epsilon W plus 1 over epsilon plus partial derivative with respect to x. And then we have the quantity in square brackets in 4.31. Vt becomes epsilon Wt using equation 4.34. And then we get plus 6 lambda minus v squared. We calculated lambda minus v squared earlier here. So that gives minus 6 W plus epsilon squared W squared, which multiplies Vx, which is epsilon Wx. And then we have Vxxx, which is epsilon Wxxx equal to 0. So the KdV equation for U, or equivalently 4.31 for V, becomes the following differential equation. So let's multiply the differential operator by epsilon and divide the quantity in the square bracket by epsilon. So we get 1 plus epsilon d by dx plus 2 epsilon squared W. That acts on Wt minus 6 W plus epsilon squared W squared Wx plus Wxxx equal to 0. That's equation 4.36. And in particular, any W that solves the differential equation obtained by setting the quantity in the square brackets to 0, namely Wt minus 6 times W plus epsilon squared W squared times Wx plus Wxxx equal to 0. Produces a KdV field U that solves the KdV equation by the Gardner transform. 4.35. So if we plug in W that solves 4.37 in the Gardner transform 4.35, we get the U that solves the KBV equation. Good. We'll stop here for today, and next time we'll see how the Gardner transform is useful to find conservation laws for the KBV equation. I remind you that we have a problems class tomorrow afternoon on Zoom, so see you tomorrow.